All right. So now we're going to actually get to prove that what the derivative of a log function, a log of any base. I'm going to start out with a specific base, log base 2. So the first thing that we're going to do is we're going to write the equivalent exponential statement. So if y is log base 2 of x, then 2 to the y is equal to x. Let's see that. The function y is log base 2 of x, and the function x is 2 to the y are in fact the exact same function. Those are equivalent statements to each other. So now I'm going to use implicit differentiation. What's step 1? I'm going to take the derivative of both sides with respect to x. The derivative of 2 to the y is equal to the derivative of x. The derivative of 2 to the y is 2 to the y times the ln of the base, ln of 2, chain rule times the derivative of y, which is y prime, right? This is just like taking the derivative of 2 to the x. That would be 2 to the x times ln of 2. Chain rule, the derivative of x with respect to itself is 1, right? It's the same thing, but instead of having an x right there, we have a y. Got to hit this with a y prime. And the derivative of x with respect to x is just 1. That's my right-hand side of the equation. Step 2, go ahead and solve for pink. Solve for y prime. So what's happening to y prime? It's just being multiplied by two things, multiplied by 2 to the y and ln of 2. So I'm going to go ahead and just divide both sides by that, and we get y prime is equal to 1 all over 2 to the y times the ln of 2. Now the original statement, we knew what y was explicitly in terms of x. Y is log base 2 of x. So if I make that substitution, then I'm going to have y prime in terms of x alone. Let's do it. Y prime is 1 all over 2 to the y. Well, y is log base 2 of x times the ln of 2. And 2 to the log base 2 of x is just x, and we are done. Y prime is 1 over x times ln of 2. So in general, we did this specifically for base 2, but if y was log base b of x instead of a 2, we'd have 1 over x times ln of the base, ln of b. The derivative of log base b of x is 1 over x times the natural log of the base. That's just a number. B is a number, so ln of b is a number. Now, the natural log function is delightful. Let's use this derivative rule. Y is ln of x. That's y is log base e, 2.7 roughly, of x. Well, y prime, with this rule, what's y prime? It's 1 over x times ln of the base, and the base is e. Sorry about that. and the base is e. And ln of e is just 1. E to what power is e? E to the 1 is e. So one thing that's so beautiful about the natural log function is that its derivative is just 1 over the x-coordinate. Said another way, the slope of the tangent line at any point on the natural log function is just the reciprocal of the x-coordinate there. And that's what this image is showing us. So here I'm at the point 1, comma, ln of 1, which is 0. And the slope right here, the slope of the green line, is the reciprocal of 1, which is 1. And we can see that, up 1 to the right 1, up 1 to the right 1. At this point, 2, comma, ln of 2, the slope of this blue tangent line is the reciprocal of the x-coordinate there. It's the reciprocal of 2. It's a half, and lo and behold, that's the case. Up 1 to the right 2. Up 1 to the right 2. This point is 3, comma, ln of 3. Purple. And the slope of that purple tangent line is a third. And one more is illustrated. This point is 4, comma, ln of 4. What's the slope of the tangent line there? It's just the reciprocal of the x-coordinate. The slope of this guy is a fourth. And this Desmos animation, here's just a picture of it, but we can look at it moving. So for my natural log function, the slope is the reciprocal of the x-coordinate. So for any point a comma f of a comma ln of a, the slope is 1 over a. It's the reciprocal of that x-coordinate. And so if I play this, it's beautiful. All of those are tangent lines to the curve ln x. Excellent.